Now I'm going to solve the same system of differential equations that we wrote down for the tank problem using Laplace transforms instead of matrices. To solve this initial value problem using the Laplace transform, we start by taking the Laplace transform of each differential equation in the system. Remember that the Laplace transform is linear and has special properties regarding derivatives. So our first equation can be rewritten as S times L of Q1 minus Q1 of 0 equals 1/12 the Laplace transform of Q2 minus 1/3 the Laplace transform of Q1. And the second equation can be rewritten as S times the Laplace transform of Q2 minus Q2 of 0 equals 1/3 the Laplace transform of Q1 minus 1/3 the Laplace transform of Q2. Now for convenience, I'm going to let x equal the Laplace transform of Q1 and y equal the Laplace transform of Q2. Making those replacements and plugging in the initial conditions that Q1 of 0 equals 6 and Q2 of 0 equals 4 gives the equations S times x minus 6 equals 1/12 y minus 1/3 x, or s plus 1/3 x minus 1/12 y equals 6. And for the second equation, sy minus 4 equals 1/3 x minus 1/3 y. So negative 1/3 x plus s plus a third y equals 4. As you can see, by applying the Laplace transform, we've changed a linear system of two differential equations with two unknown functions into a linear system of two algebraic equations with two unknowns. We can solve the system we found by any method we want. Since the coefficients involve a variable s, I usually prefer to use Cramer's rule. Writing our system in matrix form, we get s plus 1/3, negative 1/12, negative 1/3, s plus 1/3 times xy equals 6/4. According to Cramer's rule, x is the determinant of the matrix 6/4, negative 1/12, s plus 1/3 over the determinant of the coefficient matrix s plus 1/3, negative 1/12, negative 1/3, s plus 1/3, which equals 6 times s plus 1/3 minus negative 1/12 times 4 over s plus 1/3 squared minus negative a 12th times negative 1/3, which I can simplify and rewrite as 6s plus 2 plus 1/3 over s plus 1/3 squared minus 1 over 36. For y, we do the similar thing. The denominator is exactly the same as it was for x, but the numerator is now the determinant of s plus 1/3, 6, negative 1/3, 4. S plus 1/3 times 4 minus 6 times negative a third over the same denominator, which I can then simplify as 4s plus 4/3 plus 2 all over s plus a third squared minus 1/36. Now we have to find the inverse Laplace transforms of these expressions. The difference of squares in the denominator looks like the transformations of hyperbolic sine and hyperbolic cosine. But since the denominators have s plus 3 squared instead of just s squared, we also need to apply the first shifting theorem to say that the Laplace transform of e to the at times the hyperbolic cosine of bt is s minus a over s minus a squared minus b squared, and the Laplace transform of e to the at times the hyperbolic sine of bt is b over s minus a squared minus b squared. Now we just need to break x and y up into pieces of these forms using that a equals negative 1/3 and b equals 1/6. Starting with x, in the numerator I have 6s plus 2 plus 1/3, but I want to get things of the form s plus 1/3 in the numerator. So the first thing I'm going to do is I'm going to factor a 6 out of the 6s plus 2 to get 6 times s plus a third, because that looks like an s minus a. And then I also want parts that look like b, so 1/6. So I'm also going to factor a 2 out of the 1/3 to write this as 2 times 1/6. Again, that's so that I have an s minus a piece and a b piece in the numerator. Then my denominator is pretty much already written the way it needs to be. We have the s minus a squared minus b squared to match the denominator of our Laplace transforms at the top. Now, splitting this up into two pieces, I have the first fraction, which will be 6 times s plus a third over s plus a third squared minus 1/6 squared, which looks exactly like the Laplace transform of e to the at times the hyperbolic cosine of bt, plus 2 times 1/6 over s plus 1/3 squared minus 1/6 squared, which looks exactly like the transformation of e to the at times the hyperbolic sine of bt. Doing the exact same thing for y, again, I'm going to factor a 4 out of the 4s plus 4/3 so that I get an s plus 1/3 term. And this time I'm going to factor a 12 out of the 2 to get 12 times 1/6. Again, looking for s minus a and b for my two pieces. And just like before, the denominator is already in the correct form. And then splitting it up into two halves, I now get 4 times the piece that looks exactly like the Laplace transform of e to the at times the hyperbolic cosine of bt, and then 12 times a piece that looks exactly like b over s minus a squared minus b squared, the Laplace transform of e to the at times the hyperbolic sine of bt. Now we can match up the pieces exactly with the transforms. So x, which is really the Laplace transform of q1, looks like 6 times the Laplace transform of e to the negative 1/3 t, because a equals negative 1/3, times the hyperbolic cosine of 1/6 t, because b equals 1/6, plus 2 times the Laplace transform of e to the negative 1/3 t times the hyperbolic sine of 1/6 t. And y, which is really the Laplace transform of q2, looks like 4 times the Laplace transform of e to the negative 1/3 t times the hyperbolic cosine of 1/6 t, plus 12 times the Laplace transform of e to the negative 1/3 t times the hyperbolic sine of 1/6 t. So this shows us that q1, which is the inverse Laplace transform of x, is 6 e to the negative 1/3 t hyperbolic cosine of 1/6 t plus 2 e to the negative 1/3 t hyperbolic sine of 1/6 t. And similarly, q2 is 4 e to the negative 1/3 t times the hyperbolic cosine of 1/6 t plus 12 e to the negative 1/3 t times the hyperbolic sine of 1/6 t. If we wanted, we could use the definitions of hyperbolic cosine and hyperbolic sine to rewrite our solution in a more familiar form. So the hyperbolic cosine of bt is e to the bt plus e to the negative bt all over 2. And the hyperbolic sine of bt is e to the bt minus e to the negative bt all over 2. So if we apply this, we get that q1 is 6 times e to the negative 1/3 t times e to the 1/6 t plus e to the negative 1/6 t all over 2, replacing the hyperbolic cosine, plus 2 e to the negative 1/3 t times e to the 1/6 t minus e to the negative 1/6 t all over 2, replacing the hyperbolic sine. Then, doing a bunch of simplification and distribution, we get 3e to the negative 1/3 plus 1/6 t plus 3e to the negative 1/3 minus 1/6 t plus e to the negative 1/3 plus 1/6 t minus e to the negative 1/3 minus 1/6 t, which if we combine those terms together, we get that q1 equals 4e to the negative 1/6 t plus 2e to the negative 1/2 t. For q2, doing the same thing, simplifying and distributing, we get 2e to the negative 1/3 plus 1/6 t plus 2e to the negative 1/3 minus 1/6 t plus 6e to the negative 1/3 plus 1/6 t minus 6e to the negative 1/3 minus 1/6 t. So q2 equals 8e to the negative 1/6 t minus 4e to the negative 1/2 t. And these are the same solutions that we got when we used matrix methods to solve the same linear system of differential equations.